Welcome back. Let's talk about temperature and the rate. So nearly all reactions are going to have higher rates at elevated temperatures. What this means is that if you heat a reaction up, the reaction goes faster. Now, a good rule of thumb for this is if you increase the temperature of a chemical reaction by 10 degrees C, you're going to double the reaction rate. Now, this is indeed just a rule of thumb. It is not a hard and fast rule that you can do math with or anything like that. It's just kind of a good general idea to keep in mind. There are some reactions where this is actually not true. There are some reactions where if you heat them up, they actually go slower. But those are in the minority. Most reactions, when you heat them up, they go faster. Now, the changes that are occurring here, what the increase in temperature is affecting is actually the rate constant. You might have noticed, as we've been doing practice problems, that we always specify the temperature at which a reaction is occurring. This is because you're going to have a different rate constant at every temperature. Now, normally the rate constant doesn't change too dramatically if you do just a slight change in the temperature, but there are some situations where you do actually see a pretty good jump, even with a relatively small change in temperature. And you can see something similar to that here, where you can have, so this is the temperature down on the x-axis and the rate constant on the y. And down here you don't get too big of an increase in the rate constant with some nice good jumps in the temperature. But then once you get up here up to 240, 250, you are getting pretty good change there in the rate constant. So we always have to specify the temperature at which something is happening, because it's going to have a different rate at all those different temperatures. For our purposes, usually we work at 25 degrees C, which would be 298 K. Usually. Most of our tables are at that temperature, which is the main reason why we use that temperature. So, thinking about this a bit more, we said that warmer temperatures make the reaction go faster, and part of the reason for this is that warmer temperatures make the molecules move faster. What this means is, because the molecules are moving faster, they're going to collide with each other more often, and they are going to have more energy when they collide. This is best described using what we call the collision model, which essentially states that for a reaction to occur, molecules have to collide together. So you can't just think about reactions as this thing in the ether somewhere that just happens. No, there are actual particles that have to bump into each other for there to be a reaction to occur. Some kind of a collision must occur, always. Now, this gets a little bit more complicated when we realize that most molecules, especially in solutions where they're relatively close to other molecules, they undergo something along the order of 10 to the 10 collisions per second, which is a mind-boggling number of collisions in such a small amount of time. Just in 1 second, they have 10 billion collisions. So if the collision theory says reactions occur because molecules bump into each other, and we have 10 to the 10 collisions per second, why are there any reactions that are slow? Why don't all reactions occur in a split second? Well, the answer to that is kind of mainly twofold. There's two big reasons. Reason number one is, even if you get two molecules to bump into each other, and there is a potential for a reaction to occur between those two molecules, they have to bump into each other in just the right way. So not only do you have to have two molecules where they could react, but they have to hit in just the right way so that they can react. So there's an example given here of NOCl, and it reacts with another NOCl. There is only one orientation of the molecules that results in a reaction occurring. So if the oxygens bump into each other, or if chlorine bumps into an oxygen, or you could even imagine these flipped a little bit so that the nitrogens bump into each other. Like, none of those modes of collision have even the possibility of getting a reaction. The only kind of collision that could possibly yield a reaction is if the two chlorines bump into each other. So right there off the bat, you're taking that 10 to the 10 collisions and you're whittling that down a bunch, a whole bunch. So you're going from 10 billion collisions, which is collisions with everything. I would imagine a big percentage of those collisions are bumping into things where you don't even have a chance of reacting. And then a bunch of the collisions where you're bumping into molecules where there's the possibility of reacting, you're not bumping into those molecules with the correct orientation. And so we're whittling down those numbers of collisions where a reaction is possible by a lot using this orientation factor. Things have to collide with the correct orientation. But taking that even a step further, let's say we do have two molecules. There is a chance of a reaction occurring between the two of them, and they collide in the right orientation. So we have some stars aligning here. They still have another big hurdle to jump over. And this is what we call the energy of activation, or activation energy, just whichever way you want to say it. This is a minimum amount of energy that is required to initiate a chemical reaction. You could think about this like a golfer trying to sink a putt, but there is a hill between where the golfer has his ball and the hole. If that golfer hits the ball with enough energy to make it up to here on the hill, so it's not enough to get all the way over the hill, that ball is going to roll back down. And if the golfer says, darn it, didn't get over, and he hits the ball again, and he just hits it with the exact same amount of energy, it's just going to go back to the same place and roll back down. If he does it again, he hits it up, and then it goes down, and he hits it again, it goes up, and it goes down. How many times does he have to hit it with that amount of energy to get it over the hill? There's no amount of times, right? If he's only hitting it with enough energy to get to here, it is never getting over that hill. There's a certain minimum amount of energy, specifically the amount of energy it takes to get to here, the top of the hill. You have to hit it with at least that amount of energy for the ball to have the possibility of getting over the hill and into the cup. Chemical reactions are the same way. Even if you have two molecules hit with the correct orientation, if they don't hit each other with enough oomph, if there's not enough power, enough energy in the collision, mainly to overcome the old bonds and create the new ones. You have to break the old bonds are there and form new ones. There has to be enough energy to do that, enough energy to rearrange the molecules. If there's not enough energy, then even if all the other stars align, the reaction's not going to occur. And it doesn't matter how many collisions occur with this amount of energy, unless they have that amount of energy, it's no good. You could have a billion collisions with this amount of energy, and none of them will result in a reaction because there is a certain minimum amount of energy that is required to initiate the chemical reaction. And so we usually represent this with what we call an energy diagram. So here we have on the x-axis the reaction progress. So the reaction is taking place as we go to the right. And so we start off here with reactants at some certain energy. And as the reaction takes place, those molecules go up in energy to this point here. And then if they can make it here, they then have the option of either falling back down to the reactant side or falling down to the product side. And usually the products are going to be at a lower energy than the reactants were. They don't have to be, but usually they are. And so this energy difference here, the energy difference between the reactants and the top of this curve, is the activation energy. So they have to have enough energy to make it over this hill to get to the other side. If they don't have that much energy, reaction's not going to happen. So this energy barrier exists in, it says here, almost all reactions. It really is all reactions. It's just some of them are so small that we essentially ignore them. But for our purposes, all the reactions we're going to see are going to have this energy barrier. Like we said, the activation energy is the amount of energy needed to reach the top of that hill. When it's at the top of the hill, we call that the activated complex, or transition state. So there's kind of two different names for the same thing. Usually I call it a transition state. That was the way that I was taught, but activated complex is just as correct. So the activated complex is a chemical species with partially broken and partially formed bonds. It is very high energy because of these partial bonds, and you cannot isolate a transition state. You will never have a bottle of transition state molecules. The transition state is always moving. Nothing ever stays up here. It can make it up here, it can make it up to the top of the hill, but it's never going to stop there and sit. It's either going to move back to where it was or move on to the products. Nothing ever stays up there at the top. So we have an example here of methyl isonitrile, and it is going to rearrange so that the nitrogen is not bonded to the methyl group, the carbon is bonded to the methyl group. And to do that, what it has to do is this section here essentially just starts to wiggle back and forth. It wiggles back and forth, back and forth, back and forth, until it has enough energy to make it up to the top of this activation barrier, where it is perpendicular to where the bond was before. So it used to be bonded right here, but now this group is perpendicular. That is the highest energy state. It takes a whole bunch of energy to get that molecule to this configuration. And so it's not going to stay there. It's not going to stay in that configuration. It's going to very quickly either go back to being the original reactant molecule or moving to the product. And most of the time it will move to the product if the product is at a lower energy. Okay, so we already said this, the activation energy, the difference between here and here. The frequency, which we're going to talk about in just a second, is the number of molecules that begin to form the activated complex in a given period of time. So it's essentially how many molecules are able to get to here. That is what we call the frequency. And that shows up in the Arrhenius equation, which I think we will leave for the next video. It deserves its own video. So in the next one, we will talk a little bit more about the frequency, or frequency factor, as it's called here, and how that relates to the Arrhenius equation. So see you in that next episode.